A black hole is a region in space where gravity is so intense that nothing, not even light, can escape. It forms when matter collapses into an extremely dense point, creating a gravitational pull that warps space and time. This invisible cosmic phenomenon was first predicted by Einstein's theory of general relativity in 1915. Although black holes are invisible to the naked eye, their presence is detected through their effects on nearby stars and gas. They are among the most fascinating and mysterious objects in the universe, continuously challenging our understanding of physics and the cosmos. Most black holes are formed from the remnants of massive stars. When a star many times heavier than our sun exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses inward, and if the mass is sufficient, it crushes into an infinitely small, dense point called a singularity. The outer layers may explode as a supernova, leaving behind the black hole. Other types, like supermassive black holes, may have formed in the early universe from giant clouds of gas collapsing or from the merging of smaller black holes over billions of years. The event horizon is the boundary around a black hole. It is the point of no return. Once anything, including light, crosses this invisible boundary, it is trapped forever. To an outside observer, objects falling in appear to slow down as they approach the event horizon, their image stretching and dimming over time. However, for the object itself, crossing the horizon happens instantly, without any noticeable change. This strange difference in perspective highlights how time and space are warped by extreme gravity, making the event horizon one of the most intriguing features of black holes. One of the strangest effects of black hole gravity is called spaghettification. This happens because the gravitational pull on your feet would be much stronger than on your head if you were falling in feet first. The difference stretches you out into a long, thin shape, like spaghetti, before ultimately tearing you apart. This would occur near smaller black holes, where the gravitational gradient is extreme. In supermassive black holes, this tidal stretching might not happen until you are much deeper inside, allowing you to cross the event horizon without immediately being destroyed, though your fate remains sealed. Supermassive black holes are millions, or even billions of times heavier than our sun. These giants are found at the center of most galaxies, including our own Milky Way, which hosts Sagittarius H. Their origins are still a mystery, but scientists believe they formed very early in the universe's history and grew by swallowing gas, dust, stars, and merging with other black holes. These cosmic monsters play a crucial role in galaxy evolution, influencing the motion of stars and the distribution of gas. They even shape how galaxies grow and form over billions of years. Because black holes emit no light, scientists detect them indirectly. They observe how nearby stars and gas behave, measuring the speed of stars orbiting an unseen massive object. Black holes also create powerful X-rays when gas in the accretion disk heats up while spiraling inward. In 2019, the Event Horizon Telescope captured the first ever image of a black hole, U.S. shadow in the galaxy M87, providing visual proof of their existence. Advanced instruments now help astronomers study black holes with greater precision, turning these once purely theoretical objects into observable and measurable parts of our universe. Black holes dramatically affect time. According to Einstein's relativity, time slows down near strong gravity. To an observer far away, someone falling into a black hole appears to freeze at the event horizon, never quite crossing. However, for the person falling, time flows normally as they plunge inward. This concept of time dilation reveals how space and time are interconnected and warped by gravity. It also raises fascinating questions about the nature of reality and whether black holes could someday help us explore concepts like time travel, though this remains purely theoretical. One of the greatest mysteries about black holes is the information paradox. According to physics, information about matter can't be completely destroyed, but black holes seem to trap everything forever. If a black hole evaporates over time through Hawking radiation, where does the information go? Does it disappear, or is it somehow preserved? This puzzle has driven decades of research in quantum physics and relativity. Many scientists believe solving this paradox could lead to a deeper understanding of the universe, and even a unified theory that connects gravity and quantum mechanics, the holy grail of physics. Black holes often capture our imagination, appearing in movies, books, and games as mysterious portals or destructive forces. While some portrayals are exaggerated, They spark curiosity and inspire interest in space science. Films like Interstellar brought realistic depictions of black holes to the public based on actual scientific equations. Although we are far from using black holes for travel or energy, these fictional ideas push scientists to think creatively. They also highlight how much is still unknown, making black holes both a scientific frontier and a symbol of humanity's quest for cosmic understanding. The study of black holes is advancing rapidly. New telescopes and space observatories are providing sharper images and more data than ever before. Scientists hope to understand not only how black holes grow and merge, but also how they affect the universe on a grand scale. Missions like the James Webb Space Telescope and future gravitational wave detectors will reveal even more secrets. Black holes, once only theoretical, are now one of the most exciting areas of modern astrophysics, promising to unlock deeper truths about space, time, and the fundamental laws of the universe.